Welcome, guys. In this video, we are going to study increase, decrease, and concavity of functions. Let's start by defining what do we mean by increasing, decreasing, and constant functions on some intervals. Let function f be defined on an interval and let points x1 and x2 be points in that interval. Then f is increasing if on that interval if value of function at point x1 is less than value of function at point x2 whenever x1 is less than x2. So here we can see on the graph an increasing function. So if we pick two values, x1 and x2, on our input interval such that they are not equal to each other, some two distinct points, and then if x1 is less than x2, and if our function is increasing, then value at x1 is going to be less than value at x2. All right, we have similar definition for decreasing function. So function f is decreasing on the interval if value of function at point x1 is greater than value of function at point x2 whenever x1 is less than x2. All right, and our function is constant on the interval if value of function at point x1 is equal to the value of function at point x2 for all points x1 and x2 in that interval. Okay, so here is a graph for constant function. And now let's take a look at the following graph. Let's study the following figure. On the first graph here, we see an increasing function, and if we pay closer attention to the derivatives or tangent lines, slopes of tangent lines to that function in that interval, we see that all slopes of tangent lines are positive, suggesting us that if our function has positive slopes of tangent lines for all x in some closed interval, then this function is going to be increasing on that closed interval. And similarly, if we study second graph here, we see a decreasing function. And if we take a closer look at slopes of tangent lines to that function on that interval, we see that slopes of tangent lines are negative, suggesting us that if slopes of tangent lines of function on some interval, closed interval, are negative, then this function is decreasing. And in the last graph here, we have constant function. So value of function at point x is the same for all x's in some interval. And this is simply a straight line that is parallel to x-axis, meaning that slopes of all tangent lines in that interval where function is constant are equal to 0. So which suggests us the following theorem. Theorem 4.1.2, let function f be continuous on closed interval from a to b and differentiable on the open interval from a to b. If the first derivatives of function are positive for every value of x in open interval from a to b, then function f is increasing on closed interval from a to b. If first derivative of function at point x is negative for every value of x in that open interval, then function f is decreasing on that closed interval from a to b. And finally, if first derivatives are equal to 0 for every value of x in that open interval, then f is constant on that closed interval. All right, now let's use that theorem to find an intervals where our function is increasing and decreasing in the following example. Let's find intervals where this polynomial is increasing and decreasing. So first, let's start by studying the graph of this polynomial. From the graph, we can assume that our function is decreasing on interval from minus infinity up to some point. I would assume x is equal to -2 here. Then it starts again to increase on interval from -2 to 0. Then it is decreasing again up to this point x is equal to 1. So on the interval from 0 to 1, it is decreasing, and it is increasing on interval from 1 to plus infinity. Now let's confirm that using our theorem. So first we need to find first derivative of our polynomial. It is equal to 12x cubed plus 12x squared minus 24x. Now factoring out 12x, we'll have x squared plus x minus 2. Further factoring out, roots of that equation are x is equal to minus 2, x plus 2, and x is equal to 1, so x minus 1. Okay, now let's find intervals where the sign of f prime are positive or negative. So we have three roots: x is equal to minus 2, x is equal to 0, and x is equal to 1. Now, all these are simple roots, so their multiplicity is equal to 1. So we have multiplicity of 1 for x is equal to minus 2, multiplicity of 1 for x is equal to 0, and multiplicity of 1 for x is equal to 1. So all these are odd multiplicity, so we are going to use that in a second. Then let's select an arbitrary interval. Let's say we select an interval from minus infinity to minus 2. Let's choose some value from that interval. Let's select minus infinity. Then if we substitute minus infinity in our equation here, that gives us minus sign, that gives us minus sign. This is also minus sign, resulting in minus negative value for f prime. Now, using multiplicity of our roots, if we have odd multiplicity for roots, then the sign of f prime is going to change over this root. So it was negative, now it's going to be positive since 1 is odd. Now it was positive on interval from minus 2 to 0. It will switch its sign since the next root is also odd, has odd multiplicity. So this is minus. And on last interval from 1 to plus infinity, our f prime is again positive. Okay, now according to our theorem, our function is decreasing on intervals where f prime is negative. So then our function is decreasing on interval from minus infinity to minus 2. So on open at left at minus infinity and closed on right, our function is decreasing. Then our function is increasing on interval, closed interval from minus 2 to 0, since f prime is positive. And in this interval here from 0 to 1, closed interval from 0 to 1, our function is decreasing again. And in last interval from 1 to plus infinity, our function is increasing. So our function is increasing on intervals from minus 2 to 0, union with 1 to plus infinity. So I should have open bracket here. Okay, now our function is decreasing on interval from minus infinity to minus 2, union with 0 to 1. Okay, and we can confirm that by looking at our graph again. Now let's study concavity of functions. Using first derivatives, we were able to derive intervals where our functions are increasing or decreasing. Now, using second derivatives, we can find the curvature of our function. So basically, looking at the sign of second derivative, we can find the intervals where our functions are concave up or concave down. So first, let's take a look at the following two graphs, and let's give definition for concave up and concave down functions. So at the first graph here, if we pay closer attention to the slopes of tangent lines, we can see that their slopes are increasing. So they start from some large negative value, they go down to 0 here, and after this point, they attain increasingly positive value. So this function here is concave up. You can also think of that in the following way. If you pour some water in this function, then this function will be able to hold that water. And also, if you take a closer look at tangent lines again, we can see that our function on this interval where it is concave up, our function lies above all of its tangent lines. Okay, now, and concave down functions, if we start by looking at the slopes of tangent lines, we can see that their slopes are decreasing. So they start from some large positive value, they go down to 0, and they, after this point, attain increasingly negative value. And also, if you pour some water in this function, the water is going to be spilled out. And also, if the functions that are concave down on some interval, they will lie below of all of its tangent lines. Now let's take a look at the following definition. If function f is differentiable on an open interval, then f is said to be concave up on the open interval if f prime is increasing on that interval. And function f is said to be concave down on the interval if f prime is decreasing on that interval. So as we said before, we should look at the slopes of tangent lines. Now, to find intervals where slopes of tangent lines are increasing or decreasing, then we have to look at second derivatives. So we need to look for the sign of second derivative being positive or negative. And the intervals where second derivative is positive, then these are the intervals where our f prime is increasing, and the intervals where second derivative is negative, then these are intervals where our f prime is decreasing. So this theorem summarizes the following finding. Let function f be twice differentiable on an open interval if second derivative of x is positive for every value of x in the open interval, then f is concave up on that interval. And if second derivative is negative for every value of x in the open interval, then f is concave down on that interval. Inflection points. The points where our graph changes its concavity are known as inflection points. So in this graph, we can see a couple of examples of inflection points. So at x0, we can see that our graph changes its concavity from being concave up to concave down. In this example, our graph changes its concavity at x0 from concave down to concave up. So x0 here are our inflection points. Now, this is the last definition in this section. Now let's use the techniques that we learned so far to do the full analysis of the following function. Let's find intervals where our function is increasing, decreasing, intervals where it is concave up, concave down, and let's find inflection points. So first, let's start by looking at intervals where our function is decreasing or increasing. So we need to find first derivative for that. First derivative is then equal to one second, guys. So we can see the graph of our function here. We can then use it to confirm our findings. So f prime is equal to 3x squared minus 6x. So factoring out 3x, this is x minus 2. So the two roots of first derivative are 0 and x is equal to 2. Now let's find intervals where f prime is positive or negative. If we substitute plus infinity here, Then this is plus, so it's plus on interval from 2 to plus infinity. Now multiplicity of roots here are 1, so the sign will alternate. So on interval from 0 to 2, f prime is negative, and positive on interval from minus infinity to 0, meaning that our function is increasing on interval from minus infinity to 0, decreasing on interval from 0 to 2, and increasing on last interval from 2 to plus infinity. So let's write this down. So f is increasing on intervals. So remember, guys, when we are studying intervals where our function is increasing or decreasing, then we use closed intervals. So f prime, f is increasing on interval from minus infinity to 0, so 0 is closed, union with 2 to plus infinity. And our function f is decreasing on interval from closed interval from 0 to 2. Now, when looking at concavity of function, we'll be using open intervals. Just memorize that. Now, to find intervals where our function is concave up or concave down, we need to study second derivative. So let's find second derivative of our function. This is equal to 6x minus 6. So 6x minus 1. All right, so now let's find intervals where second derivative is positive or negative. So now substituting plus infinity here, we find that a second derivative of our function is positive on interval from 1 to plus infinity and negative on interval from minus infinity to 1, meaning that our function is concave up on interval from 1 to plus infinity and concave down on interval from minus infinity to 1. All right, so our function f is concave down on interval from minus infinity to 1. So for concavity, when studying concavity of our function, we'll be using open intervals. And f is concave up on interval from 1, so open interval from 1 to plus infinity. And the point where concavity of function changes is 0.1, x is equal to 1. So x is equal to 1 is inflection point. Now let's take a look at our graph and let's confirm our findings. So we can see from our graph that our function is increasing on interval from minus infinity to 0. Let's check whether that is true. That is correct. So increasing on interval from minus infinity to 0. Then our function is decreasing on interval from 0 to 2, which is true. We confirmed that by looking at the sign of first derivative. And then our function is increasing on interval from 2 to plus infinity, which is also true. Now let's study concavity of our function. We can see that our function is concave up on interval from 1 to plus infinity. And it seems that it is concave down on interval from minus infinity to this point, x is equal to 1. So x is equal to 1 is inflection point. And this is true. We've confirmed that by looking at the sign of second derivative. All right, guys, now this concludes our section 4.1 on intervals where our function is increasing, decreasing, and concavity of our functions. Thanks for watching.